Ben from electrical engineering. He's professor and dean of the College of Engineering, Technology and Physical Sciences at the Alabama University in Huntsville, Alabama, US. Okay.
Thank you very much. Got a lot to talk about. Hopefully can get as much of it in as I can into these minutes that I have. That's the outline I have. Talk a little bit about chaotic dynamics, then we talk about this transform in the context of compression, talk about it in the context of feature detection. We'll look at some of the coronal mass ejection analysis from Soho set. May hopefully have a few words to talk about hardware, although I'm not a hardware expert. I think he just left, as a matter of fact. It'd be interesting to get his take on some of this, and then we'll conclude everything. All right. So as we know, we're living in a digital age. That's why we're all here. Every experience that we have can be kind of quantified into ones and zeros, whether it's audio, visual, you name it. We're somehow experience this through digital manipulation. So this image processing is being used more and more for all kinds of analysis, and feature detection is a crucial part of that. So a consistent and reproducible kind of analysis is what's needed in order to do this, and of course you want algorithms that run quickly and are efficient. Okay, so let's talk a little bit about chaotic processes. I don't know if you're familiar with it at all, but if you're not, chaos finds itself in a lot of different situations. I'm showing an electrical circuit right here. This is a typical circuit that's been used in oscillator theory, actually not theory, but to actually design oscillators in electrical engineering. It's made to produce a sinusoid at a particular frequency, depending on what you would like to see. These are equations of motion that you see here on the left side. And if you vary the parameters, you can get it to behave in different ways. Now, I'm going to show you an example of one such behavior. If certain of the parameters fall in a certain range, this is a parametric plot or state space showing the current, the voltages versus each other. Now, if that were a sinusoid that was being generated, that would just look like a circle, complete circle through that space. But as you can see, you get variations in amplitude, but yet it falls within a constrained boundary. So there's this bounded instability that's at play when you have these chaotic processes. If you've heard about it at all, you probably heard people say it's unpredictable. Well, it's not quite unpredictable. It's predictable up to a certain point in time. Okay, so here's what they look like in time, and here's your current, your voltages in time. Now, I have purposely blocked out these different areas, and one thing you note about that is that you can get these different waveform shapes just by isolating out certain areas. And there are quite a few different or diverse shapes, I should say, within those three right there. Just that limited block of time that I'm showing. Now, so there are also many other types of chaotic systems, like the Lorentz equations, the double scroll oscillator, the Rossler system, and on and on and on. You can even put together sets of different equations that will generate these type of behavior. Now, say for instance I wanted this particular waveform. Then I would so I could say, all right, the initial condition I want is this, this, and this. I run it over this time, and I isolate that particular waveform for that amount of time, and that's the piece I have. So I could reproduce it mathematically. and the same thing for all the others. However, instead of extracting them by solving equations, I realized you could pre-store the solutions, and you could do the same thing. That was for one. But then I realized once you pre-store it, then you could do other types of things, like take different waveforms and add them together, or subtract them, do different things like that. And you could even combine waveforms from two completely different chaotic systems, or multiple, and create more diverse waveforms. And the point is to create this diversity of waveform sets, but I need a finite set because I can't have everything and all that exists in reality. It won't fit on a computer hard drive. So what we came down to was 32 waveform types of a finite length, 2 to the 16th samples, and each sample in this set that I have are 16 bits. And if I want a particular waveform, I can basically slide through here like this, specify the type, specify the position, and specify the length that I want. And I can extract different waveforms out of this finite set right here. And just incidentally, that set basically holds about 4 megabytes on a disk. Now, I also kind of ran a mutual correlation between the waveforms. This is what it looked like. As you can see, some of them correlate together now. So what you're seeing is the correlation between, waveform number 1 and waveform 1. As you can see, that's high. It's 1. It's the same waveform. And then 1 and 2 and so forth. And so you create this matrix in that way. There are, low areas of correlations, meaning that the waveforms have a difference. Now, they are not orthogonal to each other, so this ends up representing, though, an optimized set of waveforms that we can use to process thousands and thousands of distinct, different images, audio and video, as a matter of fact. Now, so what do we do here? The process is this. So we have this subject image in this case. We extract a segment from it. Those segments from this, what we call the CCO matrix, that's what this is, or that is. And then they're scaled to the minimum, maximum of the segment you pull out of the subject, and then compared to it. And all of the comparisons that are made, the one having the smallest Euclidean distance is selected, the type, the position, the length, and the scaling information is what remains and what is stored, and therefore this can be represented by 40 bits of information. So 40 bits of information that I can go back into my set that's already stored on a computer somewhere and pull out the waveform I need. So if I was to compress a segment that is length ns, then the compression ratio then is ns over 5 to 1. So here's an example. Here's a bitmap image, 24-bit color, and this is 1280 by 2048, I should say. And there's a segment, this segment was pulled out right in here. It's the green portion of the RGB image, pulled out somewhere in here. So I searched through my waveforms and found this. That was the closest to it. Okay? So with that, and the length of segment is 64 samples. And this is what I was able to get. And so in this case, the compression is 12.8 to 1. There's the decompressed image for this. I'll show you some more. I'll show you some of the peak signal to noise ratio differences as we do. But one of the things I found is that obviously it works better on the bigger image sets. because the variation is a little smoother, and therefore it does that. Now, so here's some of some of the typical images you find when you're doing this processing from this database, from USC's database. These images are 512 by 20, 512 by 512, 34. I'm taking 32 samples, so that's the compression ratio, and you can see the peak signal to noise ratio calculations from that, comparing all of these different types. This is as you go up or try to do higher and higher compression ratios. As you can see, you start to see artifacts showing up. It look like you lose about 3 dB for each time you double the length of the segments that you want to look at. Now, what I really do, I don't want to focus as much on the compression as I do on this feature extraction. Now, if you basically create and this process, we call it a D-transform. If you create a histogram, essentially, of the number of the type of segments that reside in the image, as you've done the whole process, and you go here, you find the best one, it comes from a certain type, you go next, as you scan through the whole image, you gather this collection of waveform types that are there. Turns out that this actually gives you some indication of what the image actually is. Here's the different images we're looking at. These are their profiles as a result of that processing. So we used this because I was doing some work with some images of coronal mass ejections from this solar heliospheric observatory. It's a project by NASA and some international collaboration, basically to study the sun from its deep core to outer corona, study the solar wind. It's a satellite sitting at a Lagrange point and looks at the Earth-Sun line so you can get a good picture of it. And there's different instruments. We looked at the LASCO large angle spectrometric coronagraph, and we looked at the C2 one. So this is what they look like. Here's a situation when it's fairly quiet, the sun's fairly quiet. Now this obviously is important. We're at a solar maximum right now. This study of these ejections and flares are extremely important at this juncture. And we're trying to come up with ways to actually be able to alert and have automated alerts when something is happening. So here's a picture of the sun when it's quiet. Here's one when it's there's an eruption in the second quadrant. And those particles can get sent out at very high velocity and essentially be reached in days. Now here's the D-transform profiles for each of these quadrants in this situation. Now, just quickly, the process was to process a large set of quiet zone type of thing. When these zones were quiet, get the profiles for that. And then to anything that was anomalous to that would show up in the D-transform profile. And so here's a profile of when an eruption was occurring. And here's a actually user interface that if I have time, I can actually show one running. How am I doing on time?
You have 5 minutes.
Okay, let me just see if I can run this particular example. I have it already. Well, I had it up. Let's see. Okay. So this is actually for 2010, and I'm going to just step through this, and you'll see, as you can see right right here, something's about to start to happen. This is essentially the differential of the profile that is there with the quiet zone kind of average differential that I've created prior. And when it gets significantly different, you see something happening. So let me just step through it, and you start to see this eruption occurring right there. And as we get a little closer, you can see that eruption occurring. And if you say you want to set a threshold, you could set a threshold and have an alarm go off when you reach a certain threshold on it. Okay, so let me go back. Oh, that's not what I wanted to do. Okay, so that was the example I wanted to show. So just quickly, and as far as hardware goes, this process is slow because you're taking one segment from an image. You got 3 of them. You're scanning through this whole block, finding the best one, then moving to the next one. Then you do the green one and the blue one, and then you move to the next, and next, and next, and next. All right. So, but it's very parallel. Very parallel. You can process blocks from anywhere at the same time if you're able. If you have a parallel process, you can break the image up into pieces and process them all at the same time. Because one piece is not dependent on anything else. So the process itself is very parallel. So we looked at MATLAB versions and Simulink versions, and we did some hardware development as an FPGA. Now, as I said, I'm not the hardware expert. That's the other person in my team. So I'm basically showing you some of the things that he's included into this presentation. But we're using this type of processor, the embedded processor. Here's some of the specs for it. So now, the time. Here's the processing time comparison. So for MATLAB, those images that you saw, which essentially were 256 by 256 after you broke them into their pieces, took 40 minutes in MATLAB. I have an enhanced process that I won't have time to talk about today. Then compiled C took 3 minutes. The Simulink version, which really is a MATLAB type of thing, is 34 minutes. And then the FPGA implementation took a minute for the images. And I think that is, we did not have the optimal hardware processing or architecture, so I think it could be improved even more.
Is that for the compression or the comparison?
The compression. For the compression. Yeah, the comparison is just, you take and just kind of sort how many is here. So that's very quick. We can also decompress, and it's very fast. It's the compression side. So very asymmetric. Let me conclude. So we have this process based on chaotic dynamics. We've demonstrated that this can be used to distinguish coronal mass ejections from others. Now, I want to point out here that I also use this process to identify tumors in digital X-rays. I've used it to track vehicles in video. Used it to determine from audio signals in a rotor of a helicopter when failure was imminent. So to distinguish sounds. And also I have a team of students who were looking at, I don't know, somebody might be familiar with ragas. It's a type of music in India, and they are categorized in certain different types. And we were able to take pieces of music from those ragas and place them in their specific categories. by this processing method. So there's a lot of interesting potential in all of this, and we're just trying to see what else we can do. We're going to compare other methods. There's much more work to be done in this. That's what I was talking about here. And I want to acknowledge the colleagues I've been working with. We're in some intellectual property wrapped around it. This company is the one kind of looking at that. And that's my references. So that's it.
Okay, thank you. Your questions, please.
How many different, basically, dictionaries of the chaotic waveforms did you mess with? Did you fine-tune that, or?
Yeah, I fine-tuned it. We optimized it. Here's the funny part. I'm a very intuitive kind of person, I pulled pieces from here. I figured we would need shapes that come from there, and put stuff together, put some high frequency varying ones with some smoother low frequency, and that's how I kind of intuitively put together the first set. Then I had a student do hundreds of these same sets and come up with different variations, and we optimized it. Basically took a large set of images, see which one performed the best, comparing the peak signal to noise ratios before and after. And it turned out that the one I originally started with was the one that worked the best out of all of hundreds of other sets. So to specifically answer your question, I had combinations from this Colpitts oscillator, double scroll, Lorenz, and Rossler system, and combined them together in different ways. And that's how I came up with what I did.
And then have you used GPUs at all, or looked at those for acceleration?
No, not yet. Not yet. Although a lot of the processing we did were on cluster computers and supercomputer accounts to do bunches of image at a time while you're doing a computer. So, but we knew we got to speed this thing up, and that's why we started looking at the hardware implementation.
Cool. And then I would say DNA sequence matching might be a way to leverage some better algorithms for searching for patterns.
Well, the thing I said I was going to show you that I didn't talk about just briefly was I took the waveforms that I had in my set and I classified them into families. I used something called Fourier series waveform classifications and essentially put them into families. And then my input segment, I can quickly process and say this belongs in family such and such, and then I only have to search through that group of families instead of the whole system. So that actually improved the processing 50 times. Speed it up by 50 times. So we didn't implement that in hardware yet, but we're going to. And I think we're going to see a tremendous speed improvement. So that's what we're doing.
Okay, yeah, please, short question.
Yeah, so what's so unique about this so-called chaotic dictionary as opposed compared with, say, typical different type of dictionaries you can use?
I don't know.
What's potential for it?
I think the potential is that the variation, the waveform variation that's inherent. As I told you, I mean, literally thousands of images, audio segments, video, you name it, all from that one collection of 32 waveforms. The variation to fit all of that stuff all resided in that one collection. So I think there's an enormous diversity, waveform diversity, and that's the feature of chaotic processes that I'm taking advantage of. Other than that, I'm not.
Yeah, when it comes to problem, compressional feature detection, and to prove itself to be useful dictionary, you have to use some categories, right? Based upon which you can actually prove that chaotic dictionary is better or not. From some measures. So it's not clear. Yeah, I mean like a descriptability or like orthogonality or things like that. I mean, for example, if you were to, achieve the goal of efficient compression, for example, that with Fourier basis, DCT, cosine transform basis, all those bases are very effective in terms of reducing the amount of information you have to deal with.
Right.
Then then from those type of perspectives, how can you explain that?
Well, I
choosing the
just-
chaotic basis.
Yeah, I just think that the diversity within a small space, whatever you call that space, whether it's actually hardware or it's a computer memory, whatever, that diversity within a small space is the important piece that's there. I think that's maybe what I can say to answer that question.
Okay, very short question because we
Yeah,
are...
two very quick remarks on it. Michael Barnes, I think in the 90s, proved out that you get a benefit from that. And the second thing is that your orthogonality is not necessary. Weak orthogonality will do the job for you, and
Yeah.
you still get good basics.
Okay.
Thank you for saying that, because that actually has kind of been a question and almost a contention that has popped up all over the place, that they're not orthogonal, everyone's not
You
orthogonal.
don't need to be.
And one quick thing, since you mentioned orthogonality, I was searching through my set, and I was looking for orthogonal pieces, and I found many of them. I actually found 3 mutually orthogonal. So there's 3 waveform pieces that, and they all are the same bandwidth capability.
Yeah, you're right.
And that, so now I can put 3 pieces of information, combine them together, and send them through. That's another paper that's already published.
Yeah, orthogonality is kind of one traditional way of
Yeah.
assessing.
All right, sorry.
Okay. Thank you once again.